hopefully you've had an opportunity to go over the practice problems on your own and give them a try. In this video, I'm going to go over some solutions for you. And we're going to first look at this problem where we're looking at carbon monoxide and oxygen reacting to form two molecules of carbon dioxide, or 2 moles. And so we're told that if we start with 6.7 grams of carbon monoxide and it reacts with an excess of oxygen, how much CO2 forms? So, what this phrase excess of oxygen means is it's as much as we want. So, no matter what, we'll have extra oxygen. It's not our limiting reactant. I'll abbreviate limiting reactant LR. And that means that we can base our calculations off of the 6.7 grams of carbon monoxide. So we have information about carbon monoxide, and we're trying to understand how much CO2 will be produced. So let's start with that 6.7 grams of carbon monoxide. Now, to be able to predict the amount of carbon dioxide, I'm going to do a mass to mass conversion. So this is our typical stoichiometry problem with 3 conversions along the way. Now, I can't really convert between carbon monoxide and carbon dioxide as mass. I can only do that in terms of the number of molecules because this chemical equation represents the molecules that'll be colliding with each other to form products. And so I have to do this based on a counting number. And our counting number is moles. So first I convert into moles. I'll want to make sure I don't have units of grams of carbon monoxide and that instead I have units of moles of carbon monoxide. Now from there, now that I have a number of carbon monoxide molecules, I can actually convert that into carbon dioxide because I have a prediction from my balanced chemical equation that for every 2 moles of carbon monoxide that perform this reaction, I'll produce 2 moles of carbon dioxide. So I can go ahead and convert between moles of CO2 and moles of CO. So I'm going to put the moles of CO in the bottom of my conversion factor so that way I'll be able to cancel out my moles of carbon monoxide. I've already been able to cancel out my grams of carbon monoxide. And I'm just setting this up with my units first and then I'll put in values next. And then from there, I want to report in mass. So I am going to try to convert my moles of carbon dioxide to the mass of carbon dioxide, something I can actually measure in the lab. So to do that, I'll need to make sure my moles of carbon dioxide cancel out. So I'll put that on the bottom of my conversion factor. And now I can see that those would cancel out. And I want to end with grams of carbon dioxide. So now I can go in and this will give me grams of carbon dioxide for my answer. So now I can go in and put in my values. So grams and moles, this is going to be the molar mass of carbon monoxide, which is 28.01 grams per mole. So I'll put in my 28.01 grams for every 1 mole in my conversion factor. Now my next one is going to be a mole to mole ratio, which I'll pull from my coefficients. So I can see from my balanced equation that 2 moles of carbon monoxide will produce 2 moles of carbon dioxide. So I have a 2-to-2 mole ratio for my conversion factor. And our last one is the molecular mass of carbon dioxide, which is 44.01 grams per mole. So for this one, I will plug in the 44.01 with the portion of the conversion fraction that's grams. I keep that numeric value with the grams unit, and that's per 1 mole. And I can just plug this into my calculator now that I have like a plan and I know all my units will cancel out. And when I do that, I am going to get a value that is 10.53 grams. I'm going to come and look at my significant figures here. I've got 2 sig figs in my starting measurement of mass for carbon monoxide. So I'm going to report 2 significant figures in my final answer, which is going to be 11 grams of carbon dioxide. All right, well, that's part A. So we predicted. This is, remember, this number we just predicted is our theoretical yield for the reaction. Now we're asked in part B to calculate a percent yield. So that percent yield equation again is equal to our actual mass or our actual yield that we get in the lab over our theoretical yield that we calculate using stoichiometry times 100. And our problem tells us that we've got 5 grams that we collect of carbon dioxide in the lab, experimentally, or in the lab. It kind of means the same thing. So I've got 5 grams on top. I've got 11 grams on the bottom. And I'm going to multiply that by 100 to get a percentage. When I do that, I get a value that is 45%, but I'm noting that I have just 1 sig fig. When I measured this, I just measured 5 grams. So it's a pretty, I mean, it could be 3 grams, it could be 7 grams. So I'm going to report 1 sig fig here, which is going to give me a value of 50%. All right, now let's talk about the next problem. Now in this problem, we're given a chemical reaction of methylamine reacting with oxygen. It's another combustion problem, forming carbon dioxide, water, and nitrogen. And so in this one, we are told that we have both 4 grams of methylamine and 4 grams of oxygen. We want to know how much water is produced. So we want to calculate the mass of water produced. But we're given 2 initial masses for our reactant. So this means we need to decide which is the limiting reactant. And again, we could convert just to moles and decide from there. We can also convert all the way to grams, assuming both the methylamine is the limiting reactant and the oxygen, and compare the values. So let's try it kind of both ways in this one. All right, let's start with methylamine. We're told we're starting with 4.0 grams of CH3 and H2. And we need to convert that first into moles so that way we can convert from that methylamine into another amount of a compound that's being formed, in this case, water. So our first step is to convert into moles of methylamine. So that goes on the top of my conversion. And the units that I had to start with go on the bottom. So that's grams. And so remember, this is our molar mass, which we calculate from our periodic table. And I went ahead and did this already, and in 1 mole of methylamine, it's going to weigh 31.0567 grams. All right, now we're in moles, so we can now convert between different molecules in this reaction, and we want to go to oxygen, or sorry, water. It has oxygen in it. So we're going to want to end up with moles of water, and we need to cancel out our moles of methylamine. So we're going to put that on the bottom to cancel out with this unit on the top here. So we've already canceled out our grams. All right, so now to build a conversion factor for this, I need to look at my coefficients I have. Every 4 moles of the methylamine will produce 10 moles of water based on just my balanced equation. So at this point, I could stop if I wanted and compare moles between my 2 possible limiting reactants, or I could continue on to grams. So if I stop here, this is going to equal 0.32199 moles of water. I can also choose to continue this all the way to the mass, since that's what I'll end up reporting in the end, and it's just one more step. In this case, I'm going to need to get into the mass of water. And so from moles to mass, I need to use molecular weight of water. So I would set up my conversion so I had moles of water on the bottom and mass of water in grams on the top. And so those are going to cancel out. And what I'm using here is that molecular mass of water. So for every 1 mole of water, that's going to have a mass of 18.015 grams that I calculate from the periodic table. And if I then do the calculation all the way through to mass, I'll find that I calculate a value of 5.8 grams of water. So I can either compare between moles or I can compare between mass. If I compare between moles, I'll need to still take my limiting reactant one more step to reported mass, but then it's just one more step. Okay, so we've got methylamine figured out. Let's compare it to oxygen. We're starting out with 4 grams of this as well. So I've got 4.0 grams of oxygen. And again, that first step is always making sure we go into moles. So I'll have 1 mole of oxygen is my goal, and I need to cancel out grams of oxygen. And so my molar mass is going to be 15.99 times 2. Again, we're using those weights from the periodic table. I get 31.998 grams. All right, so then I convert from my oxygen into the amount of water molecules I have in terms of moles. So I'll want to have my units of moles of water is what I end up with, so it goes on the top. And I want to get rid of these units of moles oxygen I'm currently in. So that'll go in the bottom. And now I'm looking at that coefficient in front of the water and the coefficient in front of the oxygen. So it's 10 moles of water are produced from 9 moles of oxygen. So at this point, if I stopped, my number of moles of water that I would produce would be 0.138897 moles of H2O. Now, this is coming from my oxygen as the limiting reactant, and the one above is from my methylamine as my limiting reactant. So I can compare here, right? And looking at these, the one that's smaller is the moles of water that are from my oxygen starting point. So that tells me that oxygen is the limiting reactant. So I could stop and compare moles there, but I still need a reported mass. So I'm going to take this calculation then out to units that are grams of oxygen. We can then also compare that to what we calculated for grams of water produced from methylamine. So to do this, I now need to convert from moles of water to grams of water. So my grams is on the top and my moles is on the bottom, so that they'll cancel out with the units that I'm already in of moles of water. And like we used in the previous one, it's 18.015 grams for every 1 mole of water. And when I plug this into my calculator, I get 2.6 grams of water. And if I was going to compare this one, I would compare it to the 5.8 grams of water I calculated from the methylamine. And when I compare those, the one that comes from oxygen is smaller. And so this is smaller here when compared to this one. And this one right here is smaller for my moles when compared to the moles of water that are produced from methylamine. So that means my final answer is 2.6 grams of water are produced.